It was an intense year. But how did we get here? We are 4Space from the University of Oviedo in northern Spain, and this is Trastu, our very first planetary rover. Trastu comes from a local Asturian word for mischievous, restless child. And just like a child, this project has required care, dedication, effort, and countless hours of hard work. Born from passion, built with effort, and driven by curiosity, this is our mission to go for space and beyond. 4Space is the evolution of Drone for Students, a student association founded 10 years ago at the Gijón Polytechnic School of Engineering. Since its creation, students like us have led hands-on workshops in drone design and operation, creating a collaborative, cross-disciplinary environment far beyond the classroom. In 2024, we took a major step forward. We rebranded as 4Space and set our sights on the European Rover Challenge. Today, we are 34 students from diverse disciplines: electronics, mechanics, physics, mathematics, computer science, business and economics, marketing, and more, united by one dream. Our team is structured into 6 main departments: mechanical, electronics, software, science, marketing, and management. Each department is headed by student leaders who coordinate the technical work, organize training sessions, and ensure every member grows with the project. Subsystems within the rover and drone, from power units to manipulators, are assigned to subsystem responsibles. They lead their respective developments, manage deadlines, and secure integration. This structure allows us to combine specialization with teamwork, where knowledge flows freely and new members learn by doing. But why the ERC? We choose the European Rover Challenge because it offers us a unique opportunity to promote practical education, where theory becomes reality, gain real industry experience, bring the space industry closer to Asturias, a region full of untapped potential, and foster multidisciplinary collaboration, combining diverse careers into one mission. Trastu has been designed for modularity, robustness, and flexibility. The rover is composed of its main chassis and 3 interchangeable payloads: the robotic arm, the scientific module, and the drilling unit. The chassis is entirely made of aluminum sheet metal, providing both structural strength and thermal dissipation capabilities while keeping the weight down. This is complemented by multiple 3D printed components, allowing rapid prototyping and flexibility for future upgrades. Of course, not everything always worked on the first try. For propulsion, Trastu employs high-torque brushless motors, delivering the necessary force to climb slopes and overcome obstacles. Steering is handled by 4 independent motors, allowing complete omnidirectional movement. Each wheel features an independent suspension system that ensures constant ground contact. Power is provided by 2 6S LiPo batteries operating in parallel, allowing hot swapping during operation and providing redundancy in the case of battery failure or malfunction. All power is managed through a custom-built power distribution unit, supplying independent regulated voltages for each subsystem. A dense network of sensors is integrated throughout the rover to monitor environmental, system, and mechanical parameters. To optimize space, wiring, and signal stability, these sensors have been embedded into a set of custom-designed PCBs. The rover integrates 3 Raspberry Pi boards running ROS2 Jazzy. For navigation, Trastu is equipped with cameras in all 4 directions, alongside a RealSense depth camera for accurate mapping and positioning. This visual system is complemented by odometry, wheel encoders, and high-precision RTK GPS unit to enable automated navigation and precise localization. Internal communication is handled through a combination of Ethernet and CAN bus. For external communication, the rover employs a triple redundant system. First, a 5.8 GHz WiMAX link serves as the primary long-range, high-speed channel. Second, a 433 MHz lower link provides basic telemetry and remote commands. Finally, a 2.4 GHz Wi-Fi network allows for configuration, close-range demonstration, and emergency fallback if needed. In terms of safety, Trastu incorporates an emergency stop button mounted on the top of the rover. When activated, it immediately cuts power to all actuators. To operate the rover, we have developed fully customized ground control software, which integrates deeply with the entire system. Our drone is designed for both autonomous and manual operations. This is a 7-inch class platform, balancing compact size with flight stability and performance. The total flight time averages around 20 minutes. The core of the system is a fully customized flight controller running RG Pilot firmware. For navigation, the drone utilizes a triple GPS configuration. 2 GPS receivers are mounted on the drone, one acting as the primary reference and another as backup, while a third GPS module is positioned on the ground station. This external reference remains stationary, continuously monitoring satellite signal drift and transmitting correction data. Additionally, a flow range sensor has been installed to provide precise altitude data. On board, a Raspberry Pi Zero 2W acts as a secondary processing unit. During flight operations, the drone can be controlled both via autonomous commands and via a manual override system. The pilot can take immediate control at any moment using an ELRS remote controller, which allows rapid human interaction if necessary. Through the same ELRS system, the drone also transmits telemetry data directly from RG-Pilot to the ground station. For safety, in critical situations, the drone automatically executes predefined emergency landings. Visual perception and landing zone analysis are performed by the onboard computer and camera. Real-time image processing is conducted using MATLAB algorithms, which calculate landing coordinates and analyze terrain features within a virtual grid system. The arm features 5 degrees of freedom, allowing it to reach, grasp, and manipulate objects with high precision. It supports interchangeable end effectors, enabling the team to adapt the arm for multiple mission tasks, from scientific sample collection to the operation of highly specialized tools. For safety, the system integrates electromagnetic brakes that automatically hold position in case of power loss. In the drill system, the core structure consists of an acrylic tube that provides full visual access to the drilling process. Inside, a classic helical auger drill drills into the ground, but with an added twist. Inspired by systems such as NASA's Lunar Planet Vac, we incorporated an integrated vacuum extraction mechanism. As the drill operates, loosened regolith is simultaneously extracted through suction, minimizing sample loss and contamination while increasing extraction efficiency. Collected material is transferred for precise measurement, ready for scientific analysis. Beyond engineering, our mission includes a strong scientific component, designed to simulate real astrobiology and planetary exploration scenarios. For on-site material characterization, our team has designed and built a custom Raman spectrometer. We have assembled an optical bench, a setup with kinematic mounts, and we are now in the middle of the transition to fiber optic configuration. This upgrade will be a significant advance, providing greater precision, reduced losses, and a more compact module. This custom device allows us to remotely identify mineralogical compositions and organic compounds directly at the sampling site, enabling non-destructive analysis in real time, similar to the instrumentation used in actual space missions. In addition, the astrobiology module includes a pH measurement system with a probe that ensures accurate acidity measurements. This combination of precise sampling, real-time analysis, and remote monitoring simulates the type of fieldwork planetary scientists would face during future Mars or lunar surface missions, preparing the team not only technically but scientifically as well. The proposed landing site lies adjacent to Candor Chasma, whose location and geomorphology make it compelling. Near Mars' equatorial line, it offers valuable insights into the hemispheric dichotomy. Candor Chasma's craters, plateaus, and valleys provide access to diverse geological units, enabling collection of varied samples and testing of hypotheses about Martian history and processes. More than building a rover, this project has been about growth, teamwork, and learning. Through design, testing, and research, every 4Space member's passion has driven us from Asturias to Candor Chasma, proving what a motivated multidisciplinary student team can achieve. This is just the beginning of our journey. 4Space and beyond.